Okay, if you'll turn to page 9 in your book, take a look at the chart, the top of the page. This shows vapor pressures of various hydrocarbons. It's figure 1.7. Now, nowadays, data like this is usually available in computers. It's automated, a lot of it. But looking at it in this format helps you to understand the relationships between pressure and temperature. Remember when we were talking about pressure and how pressure results from the actions of the molecules of gas colliding with each other, colliding with the walls of whatever vessel they're in. If you remember the ideal gas law, PV equals nRT. In a rigid container, if you change the temperature, you change the pressure. Because changing the temperature either slows down or speeds up the movement of the molecules, and the speed of the molecules affects how many collisions you have, and the number of collisions that you have affects the pressure. The higher the temperature, the more energy the molecules have, the faster they move around, the more they collide with each other and the walls, and the greater pressure they exert on the walls of the container, because the pressure results from the collisions of the molecules. So what this figure is showing is, for any given chemical, how the pressure of that chemical is related to temperature. And you'll notice for all these green lines, there's a chemical that's associated with those. At the top you have methane, here you have ethane, propane, butane, pentane, etc. If you take a look at the propane line, which is this middle line here, it comes back there. Well, first let me point out, these scales are in logarithm scales. So if you notice that they're kind of hard to read, that's why. For example, you go from 0.1 to 1, this distance is a change in 1 psi. The same size change on the chart actually goes from 1 to 10, and then 10 to 100, 100 to 1,000. So that's logarithm. Over here, it's this is a straight scale over here. Well, it's partly a straight scale. Anyway, this scale is kind of hard to read, so if you're having trouble reading it, that's okay. Logarithms are hard to read, but the main thing is that you understand the relationships. The example that's given in your book over here, propane in a surge tank at 100 degrees Fahrenheit, the vapor pressure is 190. So how did they get that? Propane, 100 degrees Fahrenheit, 190 psi. You come over here, you find propane's here, you find 100 degrees down here, you follow this line up. Now this is based on actual data of measuring pressures of propane in a vessel as you change the temperature of that vessel or container. So they put propane in a container, have a pressure gauge on it, and adjust the temperature, and then they just collect data. And these lines result from that. If you go up 100 degrees, follow that line up to the propane line. Oops, I went past it. There it is. Propane line, 100 degrees. Then you follow that straight back over to the vapor pressure line. If you can read a logarithmic scale, you can see, as the book says, that's 190 psi. So for any of these materials here, you can tell at a given temperature what is their vapor pressure going to be. An easier one to read, let's look at normal hexane at 40 degrees. So 40 degrees, this is a temperature scale, 40 degrees Fahrenheit, follow that line up to normal hexane, follow it over, that's 1 psi. Now if you take 40 degrees and follow it up to normal pentane, that's about 5 psi. At 40 degrees, hexane exerts a vapor pressure of 1 psi. Pentane exerts a vapor pressure of about 5 psi. Now what does that mean? That means pentane is more volatile than hexane. It vaporizes more easily. at the same temperature, you basically have 5 times as much pentane as you do hexane. Because hexane is 1, pentane is 5. Why is that? If you go back and look at this chart, we're comparing pentane and hexane. Pentane is more volatile than hexane because pentane is smaller than hexane. It's a smaller molecule. Smaller molecules tend to evaporate more easily than larger molecules. And if you look again at the chart on page 9, you'll notice that the smallest molecule has 1 carbon. Methane has the highest vapor pressure at any given temperature. You take any temperature, methane has the highest pressure. And if you follow these down, as you go down, the molecules get bigger. Methane has 1 atom of carbon. Ethane has 2. Propane has 3. Butane 4. Pentane 5, and on down. The bigger the molecule, the harder it is for it to evaporate. The smaller the molecule, the easier it is for it to evaporate. And the technical way to say that is that it has higher volatility. It's more volatile. If you look once again at table 1.1, the pressures we were just looking at, methane is up here around 5,000. At around 100 degrees, methane's about 1,000. Ethane's around, 5,000. Ethane's around 1,000. If you look at table 1.1, this column, vapor pressure at 100 degrees, methane is about 5,000 psi. Ethane, around 1,000, a little less than 1,000. So you need to be sure you understand how vapor pressure is related to the size of the molecule. The smallest molecule, the smaller the molecule, the more volatile it is. It means it can evaporate easier. So it's going to have more molecules that are in the vapor form. And the bigger the molecule, the harder it is for it to vaporize or evaporate. It's less volatile. It's going to have fewer molecules in the vapor form at a given temperature. These are all at 100 degrees. So that's vapor pressure. At a given temperature, how much of it has evaporated? And the more it evaporates, the more molecules it's going to have in the vapor stage, vapor phase. So the more collisions you're going to have. Remember, you increase the number of gas molecules, you have more collisions, so you have more pressure. Smaller the molecule, vaporizes more, greater number of molecules in the gas state, more collisions, more pressure.